In kinematics, we not only consider the streamline, the path line, the streak line, the velocity field, the u, v and w components in rectangular coordinates, cylindrical polar coordinates, we also consider acceleration. The next logical thing that we need to know in a given flow field is how the acceleration is behaving, or is the velocity uniform, or with time how is it affected. And therefore we just try to do, we have seen the equations already, we have discussed them. We will be using that equation to determine acceleration field of a given question, just as we did for streamlines, streak lines and path lines. So if in an example, if the velocity vector v is equal to v naught over L into x, ij are unit vectors in x and y directions, minus yj, and v naught and L are constant values. We need to determine the vector A, and from vector A here means the acceleration field. And as you know that velocity is a vector quantity and acceleration is also a vector quantity, and that is why you see these arrowheads. Sometimes the vector quantities are shown by underlining them or by showing an arrow on top of the letters that are given, trying to form a solution. So the velocity will be equal to u component into x into I is unit vector, v naught and divided by L. These are given as constants, so we will be treating them as constants, into I to j. So the u component of velocity vector is v naught over L, a constant, into x minus v naught over L into y. So these are the same values written in a separated form. Now the quantity of acceleration or the acceleration vector is equal to the total derivative of the velocity with respect to time, which is equal to partial derivative of v with respect to time, so, and plus the what we call as convective terms, u into dv by dx plus v into dv by dy plus w into dv by dz, and the v here written all the way is the velocity vector, and this is equal to, since w is 0, there is no motion in the z direction, therefore we have only the non-zero terms or the contributions coming from here. From there you can see, if this is the velocity vector, there is no t occurring here on the right hand side, so the derivative of v, partial derivative of v with respect to time will be 0, and of course the velocity component in the z direction is 0, so we write w is equal to 0, and that acceleration field therefore is equal to, we write this as a constant, partial derivative of this quantity that is given to us plus partial derivative of the y component of the velocity vector. When we differentiate them, then we obtain these quantities. They are reduced to this. You can see v naught over L is here. When we differentiate it with respect to x, this will be 1. So we will be left with this constant v naught over L. So this v naught over L into this v naught over L will be v naught over L square in the x direction, and the derivative of y with respect to x is 0 because they are independent vectors, quantities. And in the same way, we have a result for the y component of the velocity vector, and which is reduced to this. This means the acceleration component in x direction is ax equal to v naught square over L square into x. Ay, the acceleration component in the y direction, will be this. You can see the x occurring here, the y occurring here, so they will be there. Therefore, the magnitude of A, and as you know from simple algebra, the magnitude of a vector quantity is computed by taking the square root of summation of square of all the subcomponents. So the three components here will be ax square plus ay square plus az square. Az is 0, so the only non-zero terms will be from here and here. And when we substitute those values, we will have this magnitude of A as reducing to this quantity. So, and the direction of A is of course given by tangent of theta, which is ay over ax, and the quantity reduces to y over x. The velocity vector therefore is this, and its direction is this. The acceleration is this, and the direction is this one. Tangent of theta is equal to v over y over is equal to this. And when we try to plot it, this is the flow field of the acceleration field that we will observe. So what we need to do is to give the different values for, this needs to be, these are the quantities of acceleration, and this is the quantity for the velocity field. And when we try to plot them, the velocity vector is the straight line as shown. So this is the field, the velocity field shown in these lines, whereas the acceleration field is shown in dotted lines in this plot. You can try it plotting the graph in for different values of x and y that you can choose arbitrarily, but you can go back to the solution that has been produced for this particular question.